Have you ever stopped to think about why your coffee mug gets warm but the handle stays cool enough to hold? Or how your computer can crunch through tons of data without, melting? Well, the answer is this hidden force, an invisible architecture all around us called heat conduction. It's this quiet, powerful process that really shapes everything, from how we build our homes to how our gadgets work. So let's dive in and see how it all works. Okay, so here's our game plan. First, we're going to talk about what I like to call heat's invisible highway, how it actually travels. Then, we'll get into why some materials are great at moving heat and others are, well, terrible at it. After that, we'll look at the master tool engineers use to predict all of this, the heat equation. We'll see how it's used in the real world, and then we'll take a little peek into the future where things get really weird at the nanoscale. All right, first up, heat's invisible highway. To get a handle on this, we've got to understand the very basics of how energy moves through solid objects. Let's start with something super simple, something you've probably experienced 100 times. You stick a metal spoon in hot coffee, and a few seconds later, ouch, the handle is hot. But you do the same thing with a wooden spoon and nothing. It's totally fine. So what's the deal? Why the huge difference? Well, it all comes down to a process happening at a microscopic level, and it's called conduction. Think of the particles in your hot coffee like a crazy, energetic mosh pit. They're bouncing all over the place. The moment they slam into the tip of the spoon, they transfer that energy to the spoon's particles. Then that particle bumps into the next one, which bumps into the next one, in this incredible chain reaction all the way up the handle. That's conduction. Okay, but here's where it gets really cool. That microscopic chain reaction, it's not the same for every material, not even close. It turns out that every single material has its own unique thermal personality. And we have a way to measure this personality. It's a property called thermal conductivity, and we use the letter K to represent it. You can just think of K as a score for how well a material passes heat along. If it has a high K value, it's a conductor, a total superhighway for heat. If it has a low K value, it's an insulator. It's basically a roadblock. And the differences here are just staggering. I mean, look at this. Pure metals, like aluminum, have a thermal conductivity around 200. That's lightning fast. Then you jump over to something like plastic, and it's all the way down at 0.3. And then insulation foams, a minuscule 0.03. We're talking orders of magnitude of difference. This is exactly why that metal spoon gets hot, and the wooden one just doesn't. So with all these different behaviors, how on earth do engineers actually predict what's going to happen and control it? Well, they have a master tool, a fundamental formula called the heat equation. And I promise it's not nearly as scary as it sounds. Before you see any math, let's just get the main idea. At its core, the heat equation is just a fancy way of expressing one of the most basic laws of the universe, the conservation of energy. Right? You can't just create or destroy energy. It has to come from somewhere and go somewhere. The heat equation is just a really precise way of keeping the books on that energy. The way they figured this out is actually pretty clever. An engineer will imagine this tiny, tiny little box inside a material, an infinitesimally small volume. And for that one little spot, they do a perfect energy audit. How much energy is coming in? How much is going out? Is any energy being created right there? By balancing that simple budget, in, out, and generated, they can build the whole equation. And this is what you get, the heat equation, but just said in plain English. It's basically the complete story of heat for any single point in a material at any given time. It is the absolute key to predicting how and where things will heat up or cool down. Okay, so this is where all that theory hits the real world. Let's look at how these exact principles are used to solve some massive engineering challenges. Seriously, understanding heat conduction is absolutely critical for our modern world. It's how we design insulation to keep our homes warm in the winter. It's how we keep jet engines from literally melting in the sky. And probably most relevant to all of us, it's how we keep the electronics we depend on from frying themselves. Let's just zoom in on that computer example. A modern microprocessor, the brain of your computer, is doing billions of things every second. And all that activity generates a ton of heat in a space smaller than a postage stamp. If you didn't do anything about it, that chip would cook itself in seconds. So the solution is beautifully simple, a heat sink. It's basically a piece of metal with high thermal conductivity, like aluminum, that gets bolted right onto the chip. It acts as that perfect heat superhighway, pulling all that intense, focused heat away from the processor and spreading it out over a bunch of metal fins.
Then a simple fan just blows cool air over the fins and poof, the heat is gone. It's a textbook application of conduction. Now, everything we've talked about so far forms the bedrock of how we engineer things in the world we can see and touch. But something really wild starts to happen when we shrink things down, way, way down. When you get down to the nanoscale, we're talking about things just a few atoms thick, the normal rules just don't apply anymore. That thermal conductivity value K we thought of as a fixed number, it's not fixed down here. When you have a nanowire, the little particles that carry heat, phonons and electrons, they don't have enough room to bounce around like they normally would. The physics completely changes.
And that leaves us with this massive, fascinating question for the future. As our technology gets smaller, faster, and more powerful, we're entering a whole new territory for heat management. So how are we going to do it? How do you design an invisible architecture for heat when the rulebook you've used for a century no longer works? The person who figures that out is going to define the next generation of everything.